Okay, let's get started. If you haven't brought your homework up yet, please just wait till the end of lecture and bring it up at the end. Today we're going to start talking about interactions between nanostructures, and we'll talk about intermolecular and surface forces. I don't have any announcements other than the homework is due, and the next homework is due in about 2 or 3 weeks. We'll try to get it to you on Monday. Does anyone have a question or a comment about the assignment? Anything else? Okay. Then last time we talked about thermal properties, or Aaron talked about thermal properties, and we learned that thermal energy in solids is carried by energy carriers that we had discussed previously, particularly by electrons and by phonons, or vibrations in the lattice. And what we learned from heat transfer for conduction, Fourier's law, where the amount of heat transported is proportional to the geometry and the thermal conductivity and the temperature difference, or the temperature gradient, dt dx, breaks down at small length scales and at short times. And if you go down to really low temperatures and really small length scales, we actually see a practical realization of the fact that thermal conductance can be quantized, or there's a limit to the least amount of heat or quantity of heat you can transport through a material based upon the number of allowable modes of vibration of the lattice. And we saw what is a really beautiful and difficult experiment, but where researchers made that very narrow bridge along with a special microfabricated device to detect the heat transport through that structure, and saw that that reached the quantum of thermal conductance for the 16 allowable modes. And this means the sort of number of phonon modes is restricted. And we also saw experimentally that in carbon nanotubes of submicron lengths, very short lengths, we see the same thing as we did for electron transport, that we see ballistic phonon transport, meaning that a vibration can go through without being interrupted. And that means that the thermal conductivity of this structure actually scales with length, which is something you would never see at a macroscale dimension. Of course, the amount of heat that's transferred would depend on length. The resistance, the thermal resistance, would depend on length of, a bar of material if we had it. But the intrinsic property of the thermal conductivity wouldn't change. But this happens at very small scales. And perhaps, more practically over a wider range of length scales, the scattering of vibrations at boundaries can affect the thermal conductivity. And we saw for the second time the example of things like thin films, where if you scale down the thickness of a film, the conductivity can change. And this also governs the same principle is important for contact between interfaces. For example, if you're putting two materials together, the contact resistance is governed by the roughness of the surfaces, and also at the nanoscale, the sort of physical match between the ability of one material to transfer vibrations from the other material. And this can be very practically important for things like thermal interfaces. We'll see some examples after the exam when we start to talk about assembly, how, for example, dissipating heat from things like microprocessors is a real design challenge for nanostructures, because you have the idea that you could, for example, create a conformal film with a whole bunch of little contacts to give a locally very high interface conductance. And that can be bad and good. And in the case of thermoelectrics, there's also been a lot of work toward engineering the interface to, for example, independently manage thermal conductivity and electrical conductivity in the case of maximizing the ability of a material to generate electricity in response to a temperature gradient. And we therefore last time concluded what I listed as part one of the class, where we addressed the properties of nanostructures. And the goal of this is not to get deep into the physics and have you be able to solve for wave functions and dispersion relations and things like that, but to understand how and why the properties of nanostructures are different than their macroscale counterparts. And I thought it was important to address that, because that'll lead to our interest in why we want to put them together, how we make them, and then how their properties scale as we interconnect the structures themselves. It'll also let us give motivation for example, thinking about how to make particular devices from individual structures. So today we're going to begin section 2, where we're going to talk about interactions among nanostructures. And in this part of the course, we have 5 lectures. And today we'll talk about intermolecular and surface forces. And Monday we'll talk about surface energy and wetting and melting. So today we're going to talk about how atoms and molecules effectively feel each other, and how those interactions can be summed to relate to the interactions between bodies. And the bodies in our cases are things like nanoparticles or nanotubes or nanowires. And based on a simple kind of a pairwise approximation, we can add up the atom-atom interactions or molecule-molecule interactions and get a mathematical approximation for how two bodies interact. And then today we're going to talk about surface forces. Next time we'll talk about surface energy and melting. There's a subtle difference between surface forces and surface energy, and we'll, for example, see how nanoparticles can melt at temperatures way below the bulk melting point. For example, if you have a 10 nanometer particle of gold, it's going to melt at a temperature that's several hundred degrees lower than a bulk slab of gold because you have all those unsatisfied bonds on the surface. And based on the surface energy of the material, we can get a fairly good understanding of how and why that melting point is suppressed. And then we'll talk later about the electrical double layer, which is another way of just talking about electrostatic interactions between things in solution based on charge distributions. We'll talk about fluid flows at small scales, and then we'll talk about electromagnetic interactions in terms of what's known as surface plasmon resonance. And you may ask, well, what are some examples of why it's important to study these interactions? Well, they're important for synthesis and assembly. So, for example, later when we'll talk about synthesis of carbon nanotubes, for example, films of nanotubes on substrates, in some cases you might make a film of tangled carbon nanotubes, kind of looks like spaghetti on a plate, and in some cases you might make a film of vertically aligned nanotubes that some people call a forest. And between each of these nanotubes, the atoms in one nanotube and the other nanotube effectively, due to the reasons we're going to discuss today, pull on each other. And the ability to grow a tangled film or an aligned film depends on a number of things, but depends largely on the density of nanotubes you have growing at the start of the process. And if there are enough tubes such that they kind of, due to the interactions, due to the van der Waals forces, pull on each other, they form this self-aligned structure, and then they start growing upward. And that also results in nanotubes forming bundles. You might get groups of 5 or 10 or 50 of them packed together in kind of like a cable. And as you can imagine, as the growth proceeds, as the catalyst at the bottom keeps pushing upward, the tubes can push and pull on each other, and that can actually affect the morphology and the defects in the structure. So there is this coupling among structures that are close together. And the local forces, the local pressures between those, as we'll see today, are actually quite high. Another thing that we'll talk about is electrostatic interactions. So we don't only have one type of force, but we'll talk about different types of forces. And the idea of self-assembly, or in one way, engineering interactions between our building blocks so they will go together in a very particular and prescribed way, sort of by themselves. For example, take a droplet containing the structures you have and dry it on the surface, and for example, see if they can pack into a kind of crystal like this, is governed by how we engineer those interactions. So when you create a solution of particles, for example, of polymer nanoparticles or quantum dots or something, we'll learn today about how there's this, if the particles get close enough together, the van der Waals forces will cause them to attract. Well, if you want to prevent that attraction or aggregation, you might want to charge the surface so the like charges cause a repulsion. And engineering that overall interaction energy, that interaction potential curve, is important for controlling these self-assembly processes. And we'll build upon the picture in a couple lectures by adding the electrostatic piece. And then, for example, what I alluded to about surface energy and melting is, for example, important in many areas, but one area it's important is in synthesis of nanotubes and nanowires. For example, the fact that small particles of metal melt at temperatures beneath the bulk melting point governs the synthesis process. For example, why gold nanowires can be grown at temperatures below the bulk melting temperature of gold. Incidentally, when you make silicon nanowires, you have gold and silicon present, and silicon from the gas phase dissolves into the gold, and then you form a gold-silicon eutectic. But the location of this eutectic point at the nanoscale is lower than it would be if you had a bulk piece of material. So the idea of the nanostructures having a lot of surface lets us consider the effects of surface on forces, whether it's the intermolecular attractions, or whether it's electrostatics due to added charge, or whether it's the stability or instability of the surface due to the unsatisfied bonds. And that lets us kind of understand how things feel each other in different ways than they do at the macro scale. of course, all these interactions exist between larger bodies, but the fact that there's a lot less surface with respect to the volume or a lot less surface with respect to the mass means that these kind of interactions aren't as important in larger scale bodies. And there are a lot of other kind of fantasies that go from taking advantage of nanoscale interactions or the ability to create a lot of surface over small areas or small volumes. So some people fantasize that would be able to make some kind of Spider-Man suit so we could climb buildings if we, for example, made gloves that had very, very fine, compliant fingers at multiple scales such that we could get contact between a lot of these fingers and, say, a glass surface and take advantage of that large contact area and the strong van der Waals forces or the strong adhesion to give good contact. And there's been a lot of work, as we'll see, on development of these so-called synthetic gecko adhesives that essentially try to mimic what is on the finger of a gecko. This is a picture of a real gecko, like walking up glass, and we're looking through at his finger. And if you take higher magnification pictures of this, you see that there's a hierarchy of different branch structures that lets them contact the glass in large area and large numbers and achieve this effect. There's also the idea of engineering the structure of surfaces to control their wetting properties, and for example, by structuring a surface physically and chemically at micro nanoscales, you can, for example, control whether it's hydrophilic, meaning it likes water, or hydrophobic, meaning it doesn't like water, and that can have a lot of interesting applications for energy transport, heating and cooling, and so on, because you can control the interaction of liquids with surfaces. Okay, so today we'll talk about intermolecular and surface forces. We'll talk about the origin of these forces, and then we'll go through a mathematical way to sum the forces between two bodies based on these pairwise potentials, i.e. taking one atom and its interaction with another atom, or a molecule and its interaction with another molecule, and saying, well, if I know how two of them interact, then what if I say, well, one interacting with all the other atoms or molecules in another body? And then we'll apply this to calculation for van der Waals forces, and then discuss a bit about ways that surface forces are measured and also found in nature. And the readings we have up on CTools today are two chapters from Lennard-Jones book, which if you get into this topic in more detail, I really recommend this book. It's a fantastic book on all types of interaction forces between molecules and surfaces. And there's also a short research paper, which we'll see at the end of today's lecture, on biological contacts, things like gecko adhesives. And then I've added an extra paper, which is a review paper on nanoscale forces and their uses in self-assembly. And this is something whose topic spans this section of lectures and the section of lectures on assembly of structures. And it also talks about some other types of all other types of forces, for example, magnetic forces that we won't get into. But I think it's just a nice review that gives some practical examples. And you're welcome to flip through that if you like. So in Lennard-Jones' book, he introduces the book by saying that forces are what hold the universe together. And so he has this kind of nice figure of the Earth with an elephant standing on it and statues and Galileo dropping things from the Leaning Tower of Pisa. But he basically says that there are three categories of forces. There are nuclear forces, which hold the fundamental particles inside an atom, and these can be classified into so-called strong and weak forces, and these act over very, very short distances, things like very, very small fractions of a nanometer. And at the other limit, we have very long-range forces, gravitational forces that, as we know, act over extremely long distances. Why we stay on the Earth, or why the moon orbits around the Earth. And then we also have intermolecular forces that, for example, control why a liquid stays a liquid and how gas molecules interact. And these are the types of forces we're going to talk about today. And these operate on the length scale range of fractions of a nanometer to tens of nanometers. And even over that range, there are substantial differences, for example, in the forces felt between two bodies. If you had two surfaces that were perfectly flat, say they were atomically flat, and you held them a couple nanometers apart, they would be feeling an extreme pressure, many, many atmospheres between them. But if you had them, say, 10 nanometers apart, the pressure would be a small fraction of an atmosphere. And that means that at contacts between two macroscopic bodies that have a finite roughness, at the location of where the atoms actually contact, where you say have two atomic mountains contacting each other, because of these interactions, the forces and the pressures are in fact very high, and we'll see where that comes from exactly today. So if we look in the intermolecular force regime, we can classify intermolecular forces into three types. And we're going to talk today about one particular type, or a generalization of a bunch of contributions, called van der Waals forces. But we can classify these forces into electrostatic forces. So if you had two charges, and we're just considering the forces between two charges, that's what we would call an electrostatic force. And also if we had two, say, permanent dipoles, or molecules that had a polarity to them, you would also call that as giving rise to an electrostatic force. And then you can have what are called polarization forces, which occur due to dipole moments that are induced by electric fields of nearby charges. So a charge in proximity to a molecule can induce an alignment in the electric field in another molecule. And then there are also quantum mechanical forces, and these are what give rise to chemical bonding, things like due to the Pauli exclusion principle and so on. And in general, these are classified into short-range forces, like bonding forces, which can happen over a range of less than a nanometer, and what are called long-range forces, which will say happen over a distance of less than 100 nanometers. This is not the same long range as I defined, of course, in the case of gravitational forces, which are really macroscopic interactions. And what we're going to do is we're going to see a general case of a whole bunch of different force laws, and then for the case of van der Waals forces, we're going to give an example of a force law which basically lets us derive the interaction energy, or the force, as a function of separation. But for all of these cases, you typically have a force law that's inversely proportional to distance, or that the interaction energy and then the force is 1 over r to some power, and r is the separation between the two things we're talking about. And you'll always see that the exponent on this force law is greater than 3. And if this weren't the case, if your example had 1 over r cubed or 1 over r squared, the interaction energy would increase for long distances and large bodies, because as you integrated over a volume, you would get something that feels the other body more strongly as distance increased, and that wouldn't make sense. And we'll see how this practically drops out when we derive the interaction potential between two simple geometries later. So we saw previously the idea of this interatomic potential when we talked about mechanical properties, and we drew a very general picture of interaction energy, which can be called U, and sometimes you'll see it called V, and sometimes you'll see it called W. Just remember the distinction between energy and force, and we'll be all right. And this curve is generally, for example, U, the energy in, say, joules, as a function of separation, r, where now separation could be the distance between the surfaces of two bodies. And now I'm going to just say they're two spheres, but we'll see later these can be two planes, say two infinite half spaces, and so on. And there's kind of a little difference here. Before I talked about the distance between the centers, but today we'll be typically talking about the difference being the distance between the two surfaces of the bodies. So, whether this represents a molecule or represents two particles, meaning two larger bodies, this curve can have a different shape. And we'll see examples today of how the shape can change based on the geometry and based on whether this is U representing the interaction energy, or F representing the interaction force, or the first derivative of the energy. But this, when the potential energy is a minimum, we typically call this our sort of equilibrium separation. And then on this side, we have typically an attractive force, and on this side we typically have a repulsive force. Meaning, if we look at the force as the first derivative, the slope of this curve is negative on this side and it's positive on this side. So if we took the derivative of this, we would get a curve which tells us the force. So if U is the potential in joules, then du, say, dr, or du dz, depending on what we define as our distance, is the interaction force in newtons. And typically, we'll find that U is of some very generalized form where we have a constant c divided by r to the power n. And we said before that n is always greater than 3, based on how things work out when we consider integration between two atoms over the case of large bodies. So this picture of interactions between atoms and molecules and bodies started maybe 100 to 150 years ago when van der Waals, he was actually the guy who first proposed deviations from the ideal gas law, because the ideal gas law applies to cases where the gas is relatively dilute and you don't consider interactions between the molecules. But he said, look, there's actually interactions between the molecules, and he proposed this modified form for it. And then in 1903, it was proposed by me that the interaction potential between two atoms is what was called a pair potential. And so me said that the interaction between two atoms is actually, in general, a combination of one term which is negative and one term which is positive, therefore accounting for attraction and repulsion. And therefore, if we say by decoupling attraction and repulsion that when the two are very close together, that due to the interactions among the electrons, due to the exclusion between the orbitals, the interactions are repulsive. And we say that at longer ranges, the interactions are attractive because of what we're going to call the van der Waals interactions. Then we can sum the attractive and repulsive cases. And today we're going to pretty much hang out here in the land of attractive interactions and these, quote, long-range interactions, so say 1 nanometer to tens of nanometers, and we'll talk about van der Waals attraction being a case of attractive interactions between two bodies. So back to the kind of general picture, this idea of having an interaction energy being inversely proportional to a separation applies to all types of interactions that are classified into the categories of being quantum mechanical or electrostatic or due to polarization. And so we're not going to go into all these details, but in Israel-Ashvili's book, I don't think I gave you this chapter because it's really not important for us. But whether you're considering two charges, or whether you're considering a dipole and a charge, or you're considering two dipoles, you could derive, for example, interaction energies for all of these cases. And there are a whole bunch of different cases that are formally considered throughout this discussion of intermolecular and surface forces. And today we're going to talk about what are called van der Waals forces, which are defined formally as stated here. So what's said is that van der Waals forces are the attractive or repulsive forces between molecular entities, or between, you could say, groups within the same molecular entity that are not as a result of bond formation, or are not as a result of electrostatic interactions with one another or with neutral molecules. So basically, we don't consider bonding, we don't consider electrostatics, and we consider everything else together as what are called van der Waals forces. And formally, this includes the interactions between dipoles and induced dipoles, and what are called London forces. And basically, we don't need to know all that goes into the van der Waals forces, but we just need to accept it's something that exists, and based on the properties of a material, knowing a particular constant called the Hamaker constant, which we'll learn about later, for say a metal or say a ceramic, you can then, based on the geometry and the knowledge of the law how the interaction decays with distance, we can very accurately calculate these for different shapes. So in terms of a formal definition by UPAC, the International Union of Pure and Applied Chemistry, it's sort of the totality of non-specific attractive or repulsive intermolecular forces. And what's typically used to mathematically work with the van der Waals forces is what's called Lennard-Jones Potential, and it's called Lennard-Jones because Lennard-Jones is the guy who first proposed this, and it's a curve that looks like the one we've seen already and has that original formula proposed by me, but has a form where we are subtracting an attractive force from a repulsive, or an attractive interaction from a repulsive interaction, where the repulsive interaction is to the 12th power and the attractive interaction is to the 6th power. And because of this large difference in the exponents, you can see that this becomes much more prominent when you get to very short distances, and this is dominant at relatively longer distances. And today, when we talk about van der Waals attraction, we're just going to take this second term, basically c over r to the 6th, or interaction energy is negative c divided by r to the 6th, and use that to sum up the interactions between different bodies of different shapes. And this is the actual plot, and this is, for example, an empirical potential that's derived from an actual knowledge of the particular electronic structures of the atoms in a certain material. And particularly when we're talking about things like stability of materials or stability of molecules in solution, it's very much a balance between repulsive and attractive forces that we are going to talk about engineering. But we basically need to add some extra repulsive force to prevent things from aggregating together, because this potential alone would tell us that if these are, say, if this represents, say, two particles in solution, that they're going to come together and they're going to aggregate due to this attractive interaction if they are close enough together. And today we'll derive how much that force and how much that energy can actually be. So what we're going to start to do in a minute is we're going to assume that we can add interactions between the atoms or molecules in two different bodies by summing the pairwise interactions. So we're going to first imagine that we have one atom sitting out here at a distance d from a flat surface, and if we know the interaction energy between the atom out here and any atom inside this body is just negative c divided by r to the 6th, then we can basically integrate over the whole body and get an expression for the interaction energy between this one atom and this whole infinite half space. And then, well, we don't often have just like one atom hanging out here. What we typically have is, say, two bodies or two surfaces. So then we can just kind of repeat the integration. Once we know the energy, the interaction energy between the atom and the surface, the total surface or the total body, then we can sum up all the atoms in the body, and we can get a total interaction energy between the two. And this neglects, for example, the fact that the interaction between one atom and another atom is affected by the presence of the other atoms around it. But it turns out practically that this geometric approach works okay for capturing the geometry, and in the end, what theory is used to derive that value of c, the constant, accounts for these interactions within the material. So when we run these calculations for real materials, we use a value of c that represents the actual properties of the material, and that's how we account for that non-ideality in our geometric approximation. Okay, so now I need to add a few slides here. And we'll see how this interaction sums up. So on the previous slide, we had this picture of say an atom out here, which is sitting at a distance capital D from the surface. And I'm going to call the distance from the atom to the surface d, and then the total distance we're going to call z. And we're going to calculate the interaction between this atom and between a small volume inside the surface, which is at another distance x from our, so x is this distance here. but I'm just drawing it out. X is this distance up from, sorry, from this line here. I drew that wrong. There we go. So x is distance up here, and z is the distance here. So the length of the hypotenuse of this triangle is the square root of x squared plus z squared. And then this has width dz and height dx. And this is a solid. So now we're just going to sum things together. So we can say that the total interaction potential is just the integral over the volume of our individual per particle interaction potential times the density times dV. And here rho is a number density. So it's, let's say, the number of particles per volume. And I'm probably going to be inconsistent and sometimes say particle and sometimes say atom, but you know, we end up between the two bodies, and we're talking about summing the little dots here. So this is basically counting the number of particles and summing up the interactions among all of them. And then our little w here is the potential interaction per particle, which is minus c divided by r to the nth. And our r, our distance here between this one and any one in the body, is our hypotenuse square root of x squared plus z squared. So now let's define our differential dV, and we can do that because we want to consider all the particles inside the body that are equidistant from the one sitting outside. So that is just a dV, which is an annulus, which has volume dz times the circumference of a circle like so, which would just be 2 pi x times dx. So now our dV is 2 pi x dx dz. So now we can start filling out this integral as w being the integral over volume of w rho dV as minus 2 pi rho c, we can bring all the constants out front, times the integral over the body of going from d to infinity in the z direction times dz, and from 0 to infinity in the x direction times x divided by the square root of x squared plus z squared dx. And so now let's take a step back and see where this came from. We had, and this should all be to the nth power. So we substituted r equals our hypotenuse on the bottom of the force law. We collected the x from dV and put it in the integral by x here. And then, because x can stand alone and because we'll get something as a function of z, when we do the first integral, we integrate in x first and then we integrate in z. And all the constants came out front like so. And then we can just change our format for the square root here as being just x squared plus z squared to the power n over 2. And then if we look at the integral of this alone, we'll see that the integral of x divided by x squared plus z squared to the n over 2 dx is 1 over n minus 2 times x squared plus z squared to the n over 2 minus 1. Because we'll get a 2, we'll get an n over 2 minus 1, and then we'll get a 2 when we are integrating with respect to x, and that'll make this n minus 2, and then we're just subtracting 1 from the exponent over there. Okay. So now we have a next step that w is equal to minus 2 pi rho c times d to infinity dz, multiplied by the quantity we just derived from the integral, all from 0 to infinity. So if x is equal to infinity, this will be 0, so we just need to consider negative of this expression evaluated when x is equal to 0. So now this can become 1 over n minus 2 multiplied by z squared to the n over 2 minus 1. And then z squared to the n over 2 minus 1, you just multiply the exponents, and we get z to the n minus 2. So then this altogether equals 2 pi rho c, and we have a negative sign here, and the negative signs cancel, divided by n minus 2, because n doesn't depend on z, we can bring it out, times the integral from d to infinity of 1 over z to the n minus 2. Which then equals 2 pi rho c over n minus 2 times 1 over n minus 3, subtracting 1 from the exponent there. And then we have 1 over z to the n minus 3 from d to infinity. And then, because infinity to the n minus 3 is still going to be very large, then this term will drop out, and we're going to recover a negative sign again and just have minus 1 divided by d, our separation, to the power n minus 3. So that gives us our final answer, that the total interaction energy between our molecule or our particle and the whole big surface is minus 2 pi rho c divided by n minus 2 times n minus 3 by 1 over d to the power n minus 3. So now it kind of popped out why, if we have d to the n minus 3, then always n is greater than 3. If n was equal to 3, this would be 1 over d to the 0, which would be 1, and then the interaction energy would be independent of separation. And if d were less than 3, then the interaction energy would grow with separation, which doesn't make sense. So in the case of our van der Waals attraction, where we say, I'll call this W van der Waals is equal to some constant divided by the separation to the 6th, or c over r to the 6th. Basically, we have n equals 6. So then W of d, we can substitute n equals 6 in here, would just be minus pi rho c divided by 6 d cubed, because we would have 4 times 3, so, and then 2 would be 2 over 12, 1 over 6, and then d to the n minus 3 is d cubed. So this is our van der Waals attraction energy between a small thing and a big flat thing, if the van der Waals attraction potential is represented by a constant divided by r to the 6th. So now let's go one step farther. And now we're really interested in the simplest case, is not between one particle and a body, but between, say, two planar bodies. So now imagine that our little guy from before is somewhere in one body, which is separated from another body by a distance d, and basically we're going to take differentials of unit area and equidistance from one surface to the other. So now we can define z as being the distance from our fixed body to a planar slice in another body, and we're gonna sum the interaction energies between our surface and all the molecules that lie at that same distance. And so now we're going to, for example, say that this differential has a height L and has the width dz, and we're going to do this for a unit area. So we're going to end up with the interaction potential between two flat surfaces on a unit area basis. And then based on the area of our surfaces, we'll be able to multiply that by the real area. So then our dV is just going to be this unit area multiplied by dz, and therefore the total energy would be the integral over the volume of the unit area times our number density rho times dz multiplied by what I'm going to call our particle surface interaction, which is basically the result from the previous slide. So essentially we're just integrating once more to sum over all the particles that would be in this other body. So in terms of a general form, this would just be W per unit area. And we can say this is minus 2 pi times c times rho squared divided by n minus 2 times n minus 3 times the integral from d to infinity of dz divided by z to the n minus 3. So now z is the distance we're concerned with. Everything is the same distance from the body, so we're taking care of that by dividing by the unit area and just integrating in one dimension from d to infinity all the way into the body. And we have rho squared because we have another factor of the density when we do our differential volume in this case. And then the rest is just our final answer from the previous slide before we substituted the exponent of 6 for the van der Waals interaction. And then we'll end up substituting 6 again, but we wanted to do this in a bit of a more general basis. And then if we do this integral, it'll just be the straightforward case now of doing z to the n minus 4, and the infinity is going to go away. So that means we're going to have a result of minus 2 pi times c rho squared divided by n minus 2, n minus 3, and we get another one, n minus 4, times 1 over d to the n minus 4. So as our exponent on d gets smaller, and a 1 over d to a lower power is a function that decays over a longer distance. So we can see that as the dimensionality of our problem increases, as we go from kind of molecule-molecule or atom-atom to body and body, we end up recovering this attraction or this interaction over a longer range of distances. So even if the distance over which two molecules feel each other is relatively short, the distance over which two bodies, or say 2 nanotubes or 2 nanoparticles, feel each other is relatively longer because you sum up the interactions between all those different molecules or atoms within the bodies. Give this one more slide. So if we substituted in the previous equation for WD for which we'll call the plate and the plate, and this is for van der Waals, we have minus pi c rho squared divided by 12 d squared. So difference here, other than numerical constants, is that we're squaring the density up here, and our exponent on d is different. Otherwise, things look pretty much the same. And then, if we recall, that force is just the first derivative of the potential, which can be dw dz, or in this case is dw d big D, which is our separation. Then, for the case of a plane and a plane, we have that the force is just dd of minus pi c rho squared, that's a c, divided by 12 d squared, which would be minus pi c rho squared divided by 6 times d cubed. So we get an up in the exponent now once when we consider the force. Oh, here? No, so that should be positive. So this is kind of the simplest possible case where we have two flat surfaces, but typically surfaces aren't flat. They're more complex. So maybe we want to think about what happens with curved surfaces. In general, real surfaces are somewhere in between the two. So there are some really useful geometric approximations that can be used for when we consider, for example, if we have a curved surface and a flat surface. So now, for example, let's try to think about how we would do this summation if we had a sphere against a flat. And this approximation is what's called the Langbein Approximation. And we could very well do the math for starting from the interaction between the particle and the surface. And instead of having two planes, now having two molecules. Sorry, I don't know why the pointer disappeared. There we go. It's back. Nice. And we could define a dV inside our sphere here, which is a small plane. And if we make the assumption that the radius of our sphere is much larger than the separation, then we would derive an expression for the interaction energy W as a function of D that would basically involve one further integration, kind of like doing the two integrations we did for the case of the molecule and the plane, and then we would end up with a case for n equals 6 for our van der Waals that we have rho squared again, but now we have the radius of the body on the numerator and we have the separation D to the first power on the denominator. And Israel-Achvili takes you in more detail through this, but basically what I want to end up with is a knowledge of how these geometric relations are derived, and then the ability to apply them to a bunch of different geometries. And then there is also the case of where we have two spheres that are interacting, and you can do another geometric approximation, what's called the Derg One Approximation. And in this case, we assume that we have two spheres close together, where now d, the separation, is way smaller than the radii of each of the spheres. They don't have to be equal, but it's simpler if they are equal. And now we consider locally the interaction energy between two plates. So if the spheres are so big compared to the separation that locally it's like one molecule seeing another plane of molecules, we can basically sum up the interactions between planes of different areas. And so if we go through the math for this, we can start with the laws as derived for two planes, with the assumption that the separation is much smaller than either of the two radii. And then we can do another integral that denotes the separation between these two planes as a coordinate capital Z. So now we're measuring Z as the distance between the plane in the first space and the plane in the second space. So we have Z1 and Z2. And we don't need to go through the details of how this calculation is derived, but this does a couple things for us. It lets us relate the interaction energy between these two spheres, and it also develops a relationship between the force between the bodies and the interaction energy between the bodies. And what this tells us is that we can relate the force as a function of separation between two curved surfaces as a function of the interaction energy as a function of separation between two planar surfaces. And where this becomes really useful is that when we measure these energies experimentally, it's typically easy to measure the interaction between two curved surfaces. So you can create curves of materials much more easily than you can create and quantify very flat surfaces of materials and guarantee that they're separated very accurately at these very small scales. So by this approximation, we can relate the force as a function of separation for two curved surfaces, f of d here, to a factor that corresponds to the geometry of the two curved surfaces and the interaction energy between two planes. So what this represents is this is for two planes as we defined before, and then this f of d is the force for the curved surfaces with R1 and R2. And what this approximation does is it relates it to the f of z, which this is the force law for the planes. And the rest is just the geometry of the separation between them. And it can be shown that this applies to any force law. So basically, regardless of what the exponent is on the denominator, as long as this geometric condition of the spacing being smaller than R1 and R2 applies. So now let's look at some examples of different types of curves. And what we want to see is, for example, how the interaction, the force between two curved surfaces or the energy between two flat surfaces might compare to the force between two flat surfaces. And how we get these different curves, for example, the ones with funky minima and maxima in the curve, is not as important for us now. We'll learn about that later, but I just want to see how things can change based on the geometry and whether we're looking at a force or an energy. So now, for example, if we consider the curve at the top left here, so we're considering that this is the force between two curved surfaces, or it can, for example, represent the energy between flat surfaces by the approximation we had on the previous slide. So in the case of when we have an energy, then the equilibrium point in the case of the energy is the minimum like so. And if we're relating this to a force between two flat surfaces, we can say that this will result in a crossing of the x-axis. And if we take the full derivative, the curve will look like this. And if we have a curve that starts out looking like this in one space and we take a derivative like so, the first derivative will be 0 here and will be 0 here, and we'll end up with a relationship that looks like that. And then in the case of a curve like this, this curve can transform like that, where we'll have 3 equilibrium points corresponding to local maxima and minima in the interaction energy. And this says, for example, how how the energy curve can relate to the force curve when we're talking about flat surfaces, or how, because of how the forces and interactions scale with geometry, how the shape of the force profile between the same materials which are curved can be different than the same materials which are flat quite differently. So, for example, if we say that this is the force between two cylinders, or that would be R1 is R and R2 is infinity, or between two spheres, we will can have great differences in the shape of the two curves. And in this case, if the force between two curved surfaces looks like this, where there never is an attractive force, if we simply change the or there never is an attractive force, if we simply consider flat surfaces of the same material, because of the geometry, we will actually have an equilibrium separation between the two. And we could go through and do similar things, and some more are done in the book, and then this table is presented that presents the interaction energies for van der Waals forces for regular geometries. So in the case of spheres, we related that based on the Derg One Approximation, and you can see that we have 1/6d here times the factor that depends on the radii, and a constant a, which we'll call the Hammacher constant and defined in a minute. And same things can be done for a sphere and a surface, or two cylinders, or simply for two surfaces and two cross cylinders, and so on. And then we recover the simpler cases of two atoms, an atom and a surface, and for example, two chains, as we saw before. But in the case where we have two bodies of bulk material, we indeed replace our constant c with this constant a, which is called the Hammacher constant and relates directly to the properties of the material, or in fact can be calculated and then can let us have an actual value for the interaction energy and the interaction force between a couple of geometries. Yeah.
Count for hollow bodies?
For hollow bodies? Yeah, you could do same kinds of subtraction, just subtracting something from it.
Sure.
I guess it's kind of like, as we'll see next time, like we're going to talk about surface energy, and the idea of surface energy is essentially taking the attraction when the surfaces are very close, or basically, like a solid can be broken up into, say, two half solids where they're separated by a distance equal to the bond distance of the interatomic spacing. And so if you subtract the energy at that distance from the energy at a very far distance, basically how much work you would need to do to separate the surfaces, that can be related to twice what we call the surface energy. So you could consider the same kind of thing as like taking a sphere and subtracting out the center of the sphere in a similar fashion. So we can define this constant a, the so-called Hammacher constant, as being equal to, by definition, pi squared times our previous constant c times ρ1 times ρ2, where previously we assumed that when we had two bodies, the materials had the same number density. But in principle, we want to be able to calculate these interactions between two things which are different materials, so ρ1 doesn't necessarily have to be ρ2. So now, if we just flip this around and solve for c, then c is formally defined as a divided by pi squared times ρ1, ρ2. And there's a whole theory called Lipschitz Theory, which lets you calculate A based on the dielectric properties, the electromagnetic spectrum, basically the dielectric constant and the index of refraction, which both of those are complex properties that depend on the wavelength of electromagnetic radiation, basically because you have the electrons and the fundamental particles of the materials interacting with each other to generate these forces. You can look at how they interact with one another, and you can derive a number which governs how much this force will be. And we're not going to talk about how that number is derived. If you want, you can read about it, but it's not important for this class. We're going to basically look at how much it is and look at tables of these values for different materials. But so approximately, we can say that for most materials, the value of A, and because we're talking about energy, it's going to have units of energy, is about 10 to the 19 joules for two typical materials that are interacting in vacuum. So let's just, this is a good number to have in your head, although it will vary depending on the material we're looking at. But if we look at an example where we say we have two planes in contact, which I'm going to say is, say, a separation d of 2 nanometers. So granted, this means the surfaces are really flat, but this is practically the flatness of, say, highly polished silicon. And if we solve then for the force between the two, we have pi c rho squared divided by 6d cubed, which now if we substitute for A, we would have C is equal to A divided by pi squared, and now we're doing rho squared because rho 1 and rho 2 are equal. And then we have now pi rho squared divided by 6d cubed. So rho squareds cancel and 1 pi cancels, and the force is A divided by 6 pi d cubed, which is what we saw in the table on the previous slide. And so if we run the numbers for this being 2 nanometers, so 2 nanometers cubed, 2 times 10 to the minus 9 cubed is 8 times 10 to the minus 27. And then our A is, say, 10 to the minus 19. So, wow, that's a pretty big number. If we ran it out, we would get 7 times 10 to the 8th newtons per meter squared, which is 7,000 atmospheres. And that's a really huge pressure, but that's actually the local pressure between the surfaces if they are that close and in contact. So, not a lot of bodies come so close together, but it says, for example, why you get physical deformation of materials when they are in close contact. And if you, for example, had 2 perfectly clean and very flat silicon surfaces, and for example, put a water droplet between the two, and the water dried, and the surfaces came very close together, they would be really stuck, and it'd be hard to get them apart because you're taking advantage of the strength of these attractive forces, these van der Waals forces between the two materials to stick them together. So incidentally, if we ran this for not 2 nanometers by 10 nanometers, which is still really small, but a lot less unrealistic, or less of a special case, we would get that this value is about 0.05 atmospheres, which is still that's like a psi. So you could feel that pressure, but it's a lot less than this 7,000 atmospheres. But certainly this shows us that the attractive forces between atoms and molecules resulting to macroscopic bodies can be locally very high, and this can have a really practical impact on how nanostructures interact with one another. For example, if you have 2 small pieces of material that are locally very flat, it can take a lot of force relative to the area to pull them apart. So once things become agglomerated together or bundled together, like things like nanotubes, it's really difficult to get them into pieces. And based on theories, we can, for example, look up. We typically don't consider just the Hamaker constant of one material in vacuum, but we consider the Hamaker constants of, say, two bodies of the same material interacting across a medium. And in the book or in the reading, you'll see some tables that give the Hamaker constants for, for example, for liquids interacting across other liquids, and we'll talk more about kind of wetting and surface energies later, and also, for example, say quartz interacting with quartz across water, or mica interacting with mica across water, or polymers, and so on. And the reading that talks more beyond our scope about how the Hamaker constant is derived compares data, for example, from an equation that relates to the properties of the material, the dielectric constant, and the index of refraction, and then more exact solutions of the Lipschitz theory, as well as measurements of the properties from experiment. And the reading also talks about how we can take the Hamaker constants between say, one material in itself interacting across vacuum, which is typically what's calculated from this theory, and how we can get values of constants for interactions across different media. And this is an approximation, but for our purposes it works reasonably well. And, for example, it can be said that the Hamaker constant between, say, two materials, 1 and 2, is approximately equal to the square root of the Hamaker constants from the interactions of those two materials with themselves. And another one of the relations is that a material interacting with itself, so material 1 and material 1 interacting across number 3, which is a medium, is approximately equal to the expression, the square root of A11 minus the square root of A33 squared. So if, for example, you had values for, say, air, or say quartz interacting with quartz across a vacuum, and you had values for, say, water interacting with water across a vacuum, then you could calculate the value for, say, quartz interacting with quartz across water by a relationship like so. And you can do, there's a more complex combination for, say, interacting 1, 3, 2. So that would be one material interacting with material 2 across a third medium, and that's just a different combination of the Hamaker constants relating to these more elementary combinations. And this is something we'll probably see in the problem set when we ask you to calculate forces between structures of different materials in some devices. So in the last few minutes, I want to talk about a few examples of practical aspects and how surface forces are measured. And so this is a picture from a paper that actually calculated the deformation of carbon nanotubes due to van der Waals interactions with a substrate. So basically what they did by a computer model is realize that because of the, you could say, the pulling or the attraction between a flat substrate, I don't remember what this substrate is, this could be a silicon substrate, and the atoms in the nanotube, these are for single-walled nanotubes, so here the diameter is getting bigger, so it's becoming, you could say, easier to squash. You can see that because the surface pulls on the atoms all through the tube and pulls down at the sides, and then actually can feel the atoms up above, you actually result in a non-negligible deformation of the tube itself. So if this is a perfectly flat surface, this is actually what happens. The tube gets pulled down and really stuck to the surface and deformed, and this can affect its electrical characteristics and can also be important for how you might get it on the surface or get it off the surface. It means that this is a relatively strong force and interaction energy, so you can practically grip a nanotube just by having it sticking on a surface because of the strength of these interactions. And then in this case, they're doing, the chirality here doesn't really matter for us, but here now they're showing how if you have tubes of a particular diameter and you add walls, they in principle just get stiffer with respect to these van der Waals forces. So this is a balance between the mechanical properties and the van der Waals attraction, but you can see here how you get a lot of deformation for this case of a single walled tube. And another case in which this has been utilized or studied is in the case of having multi-walled tubes, where you can pull the center of the tube outside of the outside of the rest of the tube, and this is sometimes what's called a sword in sheath device, and they just used a manipulator inside a TEM to grab the end of a tube, and they also used the electron beam to kind of cut off the outer walls to blow them away. And if you look at the paper, you would see that they measured the force necessary to pull the tube out. And effectively, because of the radial balance of the interaction forces, if you looked at this end on, the force necessary to pull this out is very little and is just related to the effective sort of sliding resistance of the inside of the tube against the outside of the tube. And this is something that also, because of the energy, because of the system wanting to minimize its energy, if you let it go, it snaps back really fast. And they say it snaps back in a matter of nanoseconds. But this is kind of a self-stabilizing system because of the symmetry about which the atoms around the circle feel each other. If you had, for example, some defects or some corrugations, it would be a lot harder to pull this out than they did. So another thing, so Zrelishvili is a really well-known guy in the area of surface forces, and the reason he wrote the book is because he does a lot of research in this area, and he's probably the most well-known person for understanding and measuring the magnitudes of all interactions, so way beyond van der Waals forces, but for example, interactions between polymer chains and other types of interactions. And he, many years ago, invented an apparatus for measuring surface forces. And I won't show more today, but nowadays also AFM is used, for example, to measure surface forces, because you can relate the stiffness of the cantilever to basically what's pulling it down when you're measuring something. But his apparatus tries to measure the interaction between, for example, two crossed cylinders. And so down here, this is a picture of, say, two surfaces of the same material or two different materials that will sit down here, and where he will be able to measure the separation between them optically, so taking advantage of optical interference and looking at birefringence, he can measure the separation between the two surfaces if they're thin films on transparent cylinders vertically, and then by having the bottom cylinder mounted on very flexible springs, and you can change the spring design based on what you want to do, he can measure the attractive force between the two. So basically can move the bottom cylinder up and down and can measure the deflection of this spring, and by measuring that in relation to the separation can get these force separation relationships for these different materials. And this can be done in vacuum, or it can be done in different liquids, and it has given a lot of versatility. And he says that you can control the separation around about to 1 angstrom. So, for example, it might be possible to put in very small spacers, or by having something which can hold the surface from snapping in, but certainly once you go beyond, if there is an instability, once you go beyond the point where it's going to pull in, the surface might snap into contact depending on its roughness. Here's just another schematic of how this kind of machine operates. I have not seen one myself, but in principle, what is being suggested is that you have, for example, two surfaces, and for example, they can be very flat surfaces, or they can be surfaces with some roughness, or for example, you could put, say, some molecules in them, and you could measure the characteristics of a lubricant, and you could measure not only, say, the vertical attractive or impulsive surface forces, but you could also laterally measure the characteristics, the tribology of lubricants at very small separations. So this has led to a lot of interesting research in, for example, engineering coatings for wear and friction, or looking at polymers, for example, that are useful for, say, things like repairing knee joints and cartilage and so on. And what it gets down to is basically that the molecular configuration of the surfaces in this gap is very important to how they behave tribologically and how they interact. And you could certainly, for example, relate the van der Waals forces of the attractive and repulsive forces to how the surfaces behave in contact and how they degrade. And it just shows, as a schematic example, how different types of force behavior, as say, this upper piece is moved at a velocity over the lower piece, and as the force is measured with this spring, can be related to the characteristics of the surfaces. So the ability of these instruments to measure the practical aspects of real surfaces is also complementary to things like the theory that gives us the value of that Hamaker constant when we're assuming we just have an ideal geometry for a material and it's planar or it's spherical. And the last thing is what relates to the paper that I've asked you to read, and this is the fact that a lot of organisms and insects in nature use these types of interactions, basically attractive van der Waals forces, to climb and stick to things. And because they're relatively small in mass, they're in a favorable relationship where they can have enough surface area on their fingers to be able to support their own weight and, for example, be able to climb up glass surfaces. And in addition to that favorable, you could say, like surface area of finger to mass or to volume ratio, they also have feet or fingers that have structures that facilitate basically large numbers of small contacts. So in order to give a lot of interaction energy, to give a lot of interaction force, you need to be able to have small separations over a large area. So if your palm was just one flat thing, then you might contact whatever surface you're trying to climb at only a few points. But if your palm consists of all these little hairs that are each like little springs, like little beams that can deform when you press against the surface, then you can give yourself a large contact area. And there you have a balance between the force you need to get your little sub fingers into contact and the attractive force that comes as you press the atoms of your fingers into contact with the atoms of the surface. And this paper just talks in general about how this geometric relationship scales in nature. And basically, if you have smaller, what they're calling setae here, which is the name for the little fingers, then you can support more mass because you can establish more contact area. Or basically, to establish a large contact area, you need less deformation force to give a certain area of contact. And looking at over a bunch of organisms, beetles and flies and spiders and lizards that have a mass from beneath a milligram, a thousandth of a gram, up to, say, 10 to 100 grams, the number of these little fingers or little adhesion devices per unit area, per 100 square microns, increases. And so to support more mass, to give more total area, you need a larger number of smaller fingers to adapt the surfaces. And I think this is a good place to stop and is kind of a crossover between interactive surface forces and surface energy, which will relate basically as the energy or the work needed to peel the gecko finger off the surface, and we'll pick up on that on Monday.